Right. Good day. You're welcome to the White Academy once again. So previously on our class on adsorption isotherm, so we're able to look at specifically Langmuir isotherm. So we look at the derivations, and then from that, actually, we're able to pick a particular problem and solve. And remember very well in that last video, we made some conditions for Langmuir isotherm, which has to do with respect to a monolayer coverage. So that is, adsorption does not exceed a monolayer. So those were the things with several other assumptions that we made. Now, today we are looking at bed isotherm, PET. It's named after the scientist that came up with the derivation, and this specifically for multilayer adsorption. All right. So, which actually shows us that as the pressure increases, the rate of adsorption also increases. So we have that. So today, we just want to quickly look at, okay, how do we come about bed isotherm? Simply, it is written in this form. So the expression for bed isotherm is given as this. If this is the fractional coverage, then we have Vt over Vm is equal to Cx over 1 minus x, 1 minus c, then 1 minus cx. So this is the expression, all right? So we want to derive this. So that's our focus today. So furthermore, like I said, this is named after Brunauer, Emmett, and Tamer, okay, who came up with this isotherm. Now let's look at this. What are the various assumptions for this? So number one is that gas molecules only physically adsorb infinitely. All right? So the gas molecule just what? Only physically absorbed infinitely. Then as if that is not enough, okay? So adjacent molecules, okay, of gas only do what? Interact. So unlike Langmuir isotherm, where I said that actually it's assuming that the molecules of the gas are inert, so no adjacent interaction. But in this case, we have taken up this assumption that what? The gas molecules what? They interact with the adjacent molecules. Then as it were also, Langmuir isotherm, okay, is applicable, all right, to each monolayer. All right, so that's another thing. So Langmuir isotherm is applicable. So it means that actually we treat each layer, based on Langmuir isotherm. But don't forget this one is for multilayer adsorption. Then also the entropy of adsorption, okay, the entropy of adsorption, okay, for the first layer, all right, is higher than that of the second layer, okay, and higher ones. All right. Now, what that's telling us is that what, in terms of the entropy, or what we call isosteric entropy of adsorption, for the very first layer, which has to do with the bare surface. So let's say this is a surface, all right. So this is a surface, all right. So this is the bare surface, all right. So when actually no gas molecule is absorbed, then for the first layer, all right. So this entropy, okay, is higher than from the second layer. If this one is theta, that's first layer coverage, then this one is second layer, theta 2. So we take the bare surface to be you know, theta naught. Is that okay? So that is, take note of that. So what we're saying that the entropy of adsorption for the first layer, is higher than that of the second layer, and that for the subsequent layers, at this second layer and above, okay, second layer and above, okay, the entropy, okay, of adsorption, okay, is equal to the entropy, of liquefaction. Is that okay? So for that surface. So these are various adsorptions. Is that okay? So entropy of liquefaction or entropy of vaporization, for that surface. So we can move on now. So following these assumptions, then we can move on and see how we derive this.